Okay, today's topic is generating function. Have you learned generating functions in some other courses? Anywhere?
No, sir.
No, okay. Actually, the last time we did recurrence relations, the generating function is closely connected with the recurrence equations, so recurrence relations. So let's begin with the definition, formal definition of generating function. Okay. I already shared the note with you. However, I'm writing it again here. Let Fn n greater than or equal 0 be a sequence of real numbers right, then the formal power series fx, capital Fx, which is equal to n greater than or equal Fn xn is called the ordinary generating function of the sequence Fn n greater than or equal 0. Right? So, so if you are given any let's say real number sequence, then the associated generating function for that sequence can be defined as this. Right? Remember that this is a formal power series. What is meant by formal power series? I think you know that. I mean, if we are talking about the convergence, some power series are convergence in not in whole plane or whole real number line. It is convergence in some. Usually a power series has a radius of convergence, right? But here, when studying generating functions, unless otherwise specified, we are not considering its radius of convergence. We are just manipulate it algebraically, right? We formally define it like that, and then we manipulated it algebraically without considering any convergence. Now let's begin with some examples. Fn is equal to 1 for say all n belongs to n unit. So these are the examples. Okay, so what is that associated generating function? What is the first term for that one? You can just write down this one. When n equals 0, it is 1, right? And what is the second term of the power series? See that every coefficient is 1. Then what is the second term of the power series?
X.
X, yeah. Third one?
X squared.
What? X cube and so on. Right? Or in sigma notation, you can write it as xn. And I think this is a very familiar power series. Do you know any compact notation for that power series? Or any function? Of course, it's a Taylor or Maclaurin expansion of a function. What is that function? Can you remember? මොකක්ද මේ ෆන්ක්ෂන් එක? මේ වගේ පවර් සීරීස් එකක් දැකලා නැද්ද? මතකද? Yes. Do you know geometric series?
Yes.
Yeah. What is the summation of a geometric series? 1 r squared up to, let's say, rn minus 1. What is the formula for that one?
A times.
Yes,
So that means
a
1
is the
times
first term.
1. Yeah.
Yeah, so then 1.
1 minus r to the power n minus 1 or 1 minus r.
Yes, that's right. But now, now suppose that mod r is equal to less than 1. Right? And then what is the summation of this infinite sum? Here we are considering infinite sum, not the finite one now. What is that then?
1 over 1 minus r.
Yes, 1 over 1 minus r, because this one becomes 0 when n goes to infinity, right? That is happened only when mod r is less than 1. Otherwise, the series doesn't converge, right? Only when mod r less than 1, it is convergent. So this is the associated function for this one is 1 over 1 minus 6. Now you can see here, we don't consider any convergent issues. We just wrote down it as a formal power series. So that is the associated function for this one. Okay, now you must be familiar with this kind of, okay, let's see another one. Excuse me. Okay. Right. So let's see another one, another example. What about this one? Say Fn is equal to 1 over factorial n. Fn is equal to 1 over factorial n. N greater than or equal 0. Again, it's a very familiar one. What is the associated function for this one? Can someone tell?
Is it Taylor series?
Taylor series.
Taylor series? Taylor series of what, I mean?
E to the power x.
Yeah, e to the power x, right? It is e to the power x because e to the power x is equal to sigma n greater than or equal 0 xn over factorial n. Right? So those are the familiar one, and another one. Let's see. So both are infinite series, and also the generating functions available for the finite ones also, because the other powers or other coefficient can be considered at zero coefficient. What about this one? NCR. Say yeah. Let's say wait. Let's say NCR equal so FR is equal to NCR, not FN. Say MCR, right? That means F0 equal MC0, F1 equal MC1, and F M-1 equal MC M-1, and if M equal M CM. This is for R is equal 0 to up to M. What is the associated power series for this one actually? Where M is a natural number. M must be a natural number. Yes, what is? Can you remember it? It's a very, again, a very familiar one.
1 plus x to the power n.
Yes, 1 plus x to the power m. Binomial, right? Actually.
Yes.
Yeah, it is equal to m. Yeah, m. In the not correct it NCR, right? Must be NCR r greater than or equal 0. So I am writing it in. Yeah, NCR XR. In the not corrected one. R equals 0 to n. Right? R equal 0 to m, sorry. Right. The another one is this one actually. 0 half 1 half 1/3 1/4. Right. So the associated power series is this. Oops. Begin with the constant term is 0, so x plus x over 2 plus x squared over 2, x3 over 3 plus x4 over 4 this one. Can someone tell the associated function for this series? Are you familiar with that? Actually, it is equal to ln 1 over 1 minus 6. And yeah, if you write it in a compact notation, it's xn over n equal 1 to infinity, or one can write it as this. So this is equal to ln 1 over 1 minus 6. Right. And another one, 1 0 1 0 1 0 and so on. So what is this again? So actually you must know how to create that kind of, I mean, if you given this kind of basic sequence, you must guess what is the corresponding function for that one, right? So here, of course, it is equal to, now, if you write it, it is this, right? As a power series, if you write it, it is 1, that x term, coefficient of the x term is 0, then 1 plus x squared, 1 x4, x6, and so on. Or in compact notation, this is equal to n greater than or equal 0 x2n. What is that now? Can you guess? What is that?
Is it 1 over 1 minus x squared, sir?
Yes, it is 1 over 1 minus x squared. Good. Right. And now I can ask a reverse question like this. Can you guess the expansion of this one? What is the power series of expansion? Of course, you know that using the derivative or called the Maclaurin series or Taylor series, you can find. But without doing that, because you need, so you need the time to calculate that one. But without referring to the Taylor series or Maclaurin series, from some fundamental operation, you can derive that one. How you do that? These are some tricks to generate power series. Actually, you can get this function by differentiating which? What about this? d by dx 1 over 1 minus x.
You have to put minus
Yes.
there, right?
Sorry? Yeah,
Otherwise,
actually, this is equal to what? Minus 1 over
minus. Yeah.
1 minus x.
1 minus x squared, right? Now, using that one, can you find that expansion of this one? So that means d by dx 1 plus x squared and so on, right? So it's equal to 1 plus 2x plus
3x squared.
3x squared and so on. Right? So then what is the power series of this one? D by dx. No, actually this is plus, right?
Yes, sir. It must be plus.
Yes, that must be plus, right? So so in that case, now you can see that therefore x over 1 minus x squared is equal to x x plus 2x squared plus 3x cube plus 4x4 and so on, right? So you can write it as so this is equal to sigma n greater than or equal 1 in xn. That is it, right? And this is again for this one. It is equal to actually 1 over 1 minus cx is equal to n than or equal c to the power n xn. Right. Okay. So those are the some basics generating functions for some well-known sequences. What are those sequences? That 1, 1, 1, 1, and here the 1, 2, 3, 4, and this one for 1, 0, 1, 0, 1, 0, and this one for 0, 1, half, 1, 3, 1, 4, right? And this one for the factorials, of course, the factorials in the denominator, right? Those are the basic one. Now let's see the usefulness of generating functions. Why? Generating function are useful. So let's start with the example. The frog population of a lake grows fourfold each year. On the first day of year, 100 frogs are taken out of the lake and shipped into another lake assuming that there were 50 frogs. In the lake originally. How many frogs? In 20 years. In 30 years. In 100 years. Okay, try to solve that problem. 4 folds mean 4 times, right? If you put 1 frog in this year, you can get 4 frogs in next year. If you put 100 frogs in this year, you can take 400 frogs in next year, right? Now, at least try to find the frog population of now initially that in the 0th year they are putting how many 50 frogs in the lake, right? 50 frogs. Now calculate at least these after 1 2 3 4 calculate this frog population of those years. Initially start with 50. At the end of the first year, how many frogs?
That's hundreds.
100, yes. Yeah. And end of the second year?
300.
Sorry?
300.
How many we removing popular gross each on the each year? Yeah, the 400 folks. Then we removing how many the frog population of
hundreds.
100, right? Okay. Yeah. Then 300. Okay. Now try to find in after n years how many frogs are populations are in the n years. Can someone guess?
That's 4an minus 100.
4an minus 100.
Yeah, after n years.
What is an then? You mean 4an minus 100. What is an? Is that number of years?
N would be, no sir, it's what we get in the previous term.
Yeah, then actually, so you have a recurrence relation there, right?
Yes.
N plus 1. That's mean the N, if N is the frog population after 10 years, we can get this recurrence relation. We can build. right? We can build this recurrence relation. But the problem is, then how you solve AN? Can we find AN then? Of course, we know the initial conditions also. Now, what is AN then? You learned how to find AN from last lesson. No?
By solving the associated like the general equation.
Just associated what? First, you have to solve associated what? Yeah, you must take. You must take the closed form formula for this one. But how you get that closed form formula? How you derive that closed form formula for the AN? First, you have to build what?
First, we need to get the characteristic equation.
Yeah, characteristic differential equation, quadratic equation, right? Here, what is the characteristic quadratic equation? What is the characteristic equation for this one?
X.
X.
X minus X. X equals 4 minus 100.
X equal 4 minus 100? No.
No, sir. So it's like
Sorry?
if we take that with that 100, it's hard to find, like it comes like x to the power n plus 1 is equal to 4xn minus 100.
Actually, if you put n in is plus equal to alpha n plus 1, you can find it, right?
Yes, sir. That's what I told. It's
Yeah,
alpha
then
n
but
plus
just
1
yeah.
is equal to 4 alpha n minus 100.
Alpha n plus 1 is equal to 4 alpha n
minus 100.
minus 100. Right. Now what happened? Now what? So last time we learned to solve which recurrence relations or which yeah,
Second order linear ones.
yeah, is this a second order linear one?
No.
Sorry,
If n is equal to 1, yes, else it's
n is equal to
Which is first order.
First order.
why you say first order?
So n plus 1 minus n
Or
equals
is this
1.
a linear one?
it's not linear.
Yeah, actually it is not a linear one, right? So now we are going to use generating function to solve this kind of recurrence relations, right? Let's see how to do that. Actually, the technique is n plus 1 is equal to 4n minus 100, right? Now multiply both side by xn plus 1 and then 100 xn plus, right? Then take the summation from 0 to infinity. Now we are going to produce associated generating function for both recurrence relation. Right? Oops. Now focus on this one. Now remember that what he's saying. N is the fish population after n years, right? In this side you don't get any A0. Why? What you get up to A1? They are, that one start with A1. A1 x, A2x squared, like that, right? What is that associated power series for this sequence actually? So it is n xn, n greater than or equal 0, right? Let's say this is equal to gx. Now actually if you calculate the associated function for gx, we are done, right? gx හොයාගත්තොත් අර ඒක expansion එක ආවම මේකේ n හොයාගන්න පුළුවන්. So here, is this equal to gx? Can someone tell me, is this gx? If not,
gx minus a naught.
Yes, it is equal to gx minus a naught, right? Is equal to, what is this actually? What is this then?
4gx.
4gx. No, actually.
No. Oh, no.
Because why it is not?
Because we have the power xn plus 1.
Yeah. Then it is equal to 4x.
4x gx.
Gx, right? Minus 100. And what is this now? N greater than or equal xn plus 1. Be careful. It is this. What is the associated function for that one? You can find it easily.
X over 1 minus x?
Yes, x over 1 minus 6, right? You can take x out, then you can see x over 1 minus 6 there. So it is equal to, now from that, you can see that you can take that the common gx out. I think I don't need to do the calculation. You can show gx is equal to, and you know that this is equal to 50 also, right? So gx is equal to 50 over 1 minus 4x minus 100x over 1 minus 6, 1 minus 4x. Actually, that is the generating function for an. If you know that one, that means you know the an. But the problem is, without expanding this one, you cannot find the coefficient a, right? So of course, all the information are including in this generating function. What does that mean? Actually, the fish, not the fish, actually, frog population after n years, each n year, including in that information is includes in this generating function. But the problem is, without expanding it, we cannot practically find what is said, right? Now the next task is expanding that one. So let's see how to expand that one, right? Of course, so you can easily expand this one. Can someone tell me? What is the generating function for that one? I mean the power series for that one. 51 minus 4x. Yeah, of course, it is equal to 50 times sigma n equal n greater than or equal 0, 4x to the power n. Right? So that means 50 times xn. Right? A naught is equal to 50, right? Yeah. We know that actually A naught equal 50. Okay. Now, so that is the expansion of this one. That one. Now the expansion of this one. Can someone tell me that which trick we should do to find the expansion of this power series, this function, this expansion of that function? How we find it? I mean, without using Taylor series, how you do that? Again, we can use the geometric series, but if it is in that form, we cannot use geometric series. How you convert it to a geometric series? So, I mean, so you can use a very familiar method in A levels. What is it called? Partial fractions. Yes. So you can see that we can write. I mean, I don't need to do the calculations. You can find this is equal to, if we split it into a partial fractions, you can get this one. Please do the calculation with you. Right? So it is equal to 100 over 3. Right now, see that here the 1 minus 4x, then again you can use the geometric series. N greater than or equal 0, 4n xn minus n greater than or equal 0 xn, right, which is equal to sigma n greater than or equal 0, 4n minus 1, 100 over 3 xn. Right? Now you can see you have 4xn there, 4nxn there, and here the 4n minus 103 over xn. Now compare the coefficient by equating the coefficient. that gx is equal to this one, right? So what is gx? It is equal to sigma anxn, n equals 0 to infinity. So that means an is equal to 50 4n minus 100 4n minus 1 over 3. Okay, actually we solved that recurrence relation, right? So we found the closed form expression for the recurrence relation. Here we use that generating function technique. That's a common technique to solve that kind of recurrence relations, actually, right? So you can see actually that generating function is a very important one, because it's in a sense it's gathered lot of information. I mean, in a compact notation, it's hide lot of information, but you need or you must know how to expand that one to take out that information, right? Okay, now I will give you a problem. Try to do that one. Now, can you remember the procedure here? So let's see. Example. Let n plus 2 equal 3n plus 1 minus 2n if n greater than or equals 0. Right? Let a naught equals 0 and a1 equal 1, right? Answer. Find an explicit formula for a actually in the earlier problem using a real world scenario, we built that recurrence relation. Now they are given the recurrence relation. Now our task is find a closed form expression for this recurrence relation, right? By the way, is this a linear recurrence relation? Is this a second order linear recurrence relation?
Yes,
Sorry?
I think yes, sir.
Yeah, it is a second order linear recurrence relation. Now, if you remember to solve the second order linear recurrence relation, of course, you can find a closed form expression for this one, right? That's a one method to solve this recurrence relation. Now, you don't need to do it in this way. Now, let's find the an using a generating function method. Now, from above example, you see that the power of the generating function method, because that in earlier example, you cannot solve it using that. It is not a linear recurrence relation, right? Linear now. So there you cannot use that theorem. So you must use the generating function. Of course, here you have two options. you can use that theorem, or you can use generating function. But for the practice, so let's try to solve this using the generating function. Now, can you remember the procedure? We start with writing this one. And then what we did? We must multiply both sides by the power of this left-hand side one. That means we must multiply it by an plus 2 xn plus 2, which is equal to 3an plus 1 xn plus 2 minus 2an xn plus 2.
Excuse me, sir.
Yeah.
So is it always the we should always multiply it by the left hand one, or the term with the highest power?
Term with the highest power, actually, right?
Okay.
Usually we write, we isolated it into the left hand side, terms with the highest power,
Okay.
right?
Okay.
Because okay, yeah. Highest power means highest subscript, right?
Yes.
Yeah. So now take the summation from n equals 0 to infinity. Right. So we now so we are ready to find the generating function. Now, of course, what is gx? Our generating function, standard generating function is this one, n xn n greater than or equals c, right? According to that notation, this is equal to what? What is
Gx
that?
minus gx minus a0 minus a1 times x.
Yeah. Okay. In this problem, a0 equal 0, a1 equal 1, right?
Yeah.
Then
So gx minus x.
Yes, it is equal to gx minus x then, right? With the initial conditions. A0 0, a1 equal 1, right? With that initial condition, it is equal to gx minus x. And what is this?
That's 3x times gx.
Yes, it is 3x times gx. Okay. Some other one, please tell me what is that?
Two x squared gx.
Yes, it is 2x squared gx. Now, if you take the gx there, yeah. So, yes, so gx is equal to, you can find gx by algebraic manipulations. You can find gx directly. So that is gx, right? Now the problem is how to find the Taylor expansion or Maclaurin expansion. Of course, you may know that tail expansion theory, but again, it's a very tedious task to find the tail expansion or Maclaurin expansion from that theorem. The easiest way is using that fundamental generating function, of course. How we convert it to that fundamental ones. Of course, this is, you can write, you can see that 1 minus 3x plus 2x squared is equal to x minus 1, 2x minus 1, right? So it can be factored like that, okay? And then, therefore, by partial fraction decomposition, there are some constant a and b such that a over b over so a is equal 1 equal minus 1, right? Therefore, x over 1 minus 3x plus 2x squared is equal to minus 1, 1 minus 6 plus 1 over 1 minus 2x. Therefore, gx equal any greater than or equal 0 xn. So you can actually check the calculations, right? Here that now why I write that now here, why I wrote here this as minus 1, 1 minus x instead of 1 over x minus x, because then only then I can easily convert this into that familiar power series. It is this. Okay, that sum it's in, yeah. So they are minus 6. Yes, this is minus 6. Right? And plus, then there you get sigma n greater than or equal 0. Now 2x to the power n. That means 2n xn, which is equal to 2n minus 1 xn sigma n greater than or equal 0. Therefore, an equal 2n minus 1. And of course, you can check your answer. Compare with that theorem in linear recurrence. Relation. Of course, you can do that also. Right? Let's see another example. Let's find the Fibonacci number generating function. We know how to define the Fibonacci numbers. It is equal to Fn equal Fn minus 1. Okay, capital Fn equal capital Fn minus 1 plus Fn minus 2 for n greater than 1 with f naught equal 0 and f1 is equal 1. Those are the initial condition. Okay, the problem is prove that this generating function, say Fisher equals sigma Fn shed n greater than 0 satisfies F Fisher is equal to shed over 1 minus shed squared, right? Which is equal to 1 over root 5, 1 over 1 minus alpha shed minus 1 over 1 minus beta shed, where alpha equal 1 plus root 5 over 2 and beta is equal to 1 minus square root 5 over 2. Okay, now try to prove this one yourself. Right. Did someone complete it to this step?
Yes, sir.
Okay, let's see how to do it. Just tell me. We must multiply this one by what?
Zn.
Yes. Yes, you can multiply it by Zn. Then what?
Then take the summation.
Greater than or equal 0. Finish it then. Right?
Yes.
Okay.
Then Fz plus Z in the left hand side.
Sorry.
That's
This
Fz
one,
plus
yeah.
Z.
Efficient plus Z is equal to, they are
Z times Fz.
Oops. Shed time efficient, right? Is
Yes.
that correct?
Yes.
The problem is, what is if minus 1 then?
So in in that term, I took the summation from 1, and next term I took the summation from 2 because f minus terms are not defined.
Yes, but not define mean. Okay, you must do it in this way. Finish it then, right? You must be careful in handling that one. Not define mean we cannot assume it is 0 then. Right?
Yeah. So actually, sir, like in the problem,
Yeah.
if the Fibonacci sequence is defined as fn plus 2 equals fn plus fn plus 1, then this problem won't happen.
Then you must multiply the both side by fn plus 2, not fn actually.
You mean Zn plus
sorry,
2?
Zn plus 2. Yeah. Wait.
But still, like fn minus 1 and fn minus 2 terms are there.
Yeah. Wait. Yeah, let's take efficient. What is the efficient there? Efficient is that one, right? Right, that is efficient. So n equals 0 efficient. So this is efficient, right? Why it is efficient plus efficient? No?
So n is like here in the problem, n should be greater than 1, right?
Sorry?
In the problem,
Yeah.
So throughout the whole process, n should be greater than 1, right?
Greater than 1? No. N
Because
greater than or equal 0. F0 is there, right? F0 equals 0.
okay, so okay, yeah, okay.
Yeah. Okay. You must be careful in handling this one. Okay, let's see.
So can't we rewrite this like fn plus 2 is equal to fn plus 1 plus fn?
Sorry, Fn.
Fn plus 2
Yes.
is equal to
Yeah.
fn plus 1 plus fn
Fn.
plus 1
Yeah.
plus fn.
Plus Fn. Yeah. For n greater than or equal
Zeros.
0.
Yeah.
Yeah, that is the way we must write it. Right?
So from
So,
that we can follow what we did
yeah. So you must rearrange it in this form. Otherwise, you will get that trouble with the minus term and minus 2 terms. Sometimes you can get the answer, right? But in this problem, but it is not always happening. Sometimes you will get trouble with without proper. You cannot just neglect the minus terms. If minus 1, we don't know what is those value actually, right? I mean, they don't define, right? So actually f minus 1, we cannot take it as 0. So the better method is first you must convert it into this correct form. I mean, the correct mean the into the context. Then you can avoid that negative terms. Now you can multiply this by what?
Z to the power n plus 2.
Yeah. Okay, sorry, n plus 2 and n plus 2. Now you can take the summation. Yes, now it's, sorry, fn plus 2. Okay, now what is this? According to the definition, what is that? This is our efficient, right? Efficient equal to what? Sigma n greater than or equal 0 Fn is scheduled. Yeah, according to that definition, what is this? Yes?
F of
Sorry?
C minus C.
F of C, yes. Minus C, right? Because this is equal to, start with F2. F2, shed 2, so on. And here the F0 plus F1 shed. But F0 equals 0, F1 is equal 1. So it is equal to FC minus C. And what is this then? What is that? Yes.
ZFC.
Sorry.
ZFC.
ZFC and that
Z squared FC.
Z squared FC. Yes. Right now, you can take that FC out. Then you get minus Z Z squared plus Z minus 1, right? So FZ equal to FC is equal to, let's say the answer 1 minus Z minus Z squared. Yes, so you can write is equal to 1 minus Z is equal to Z squared. Right. Now, how you convert it to the next part? I mean, how you solve the, or how you derive this one then?
So the denominator
that.
is a quadratic equation.
Yes.
So we can use the equation to find two roots of Z, that quadratic equation.
Yeah.
Then we can write that equation as factors, like two factors.
Yes, yes, yes. That means.
But the problem is
then
like,
let's see. You can write it as Z. I think the two. What are the two roots?
1 plus or minus root 5 over 2.
Yes. Then you can factor this as what?
Z minus.
Yeah. Z minus
1 plus root 5 over 2.
Yeah, it is alpha, right? I mean the 1 minus.
Yeah.
And the other
then
one
Z
is
minus beta.
Z minus beta. Okay. Then what?
Then use partial fractions.
Yeah, you can use partial fraction because 1 minus Z minus alpha, Z minus beta is equal to B over Z minus alpha plus B over Z minus beta. Right? From that, you can find AB. I think you get A is equal to root 5. This is equal to minus root 5. You can find.
So actually,
it,
they are in the numerator. It should be Z, right?
Sorry.
In the left hand side numerator, instead of 1, it should be Z, right? Because
Instead of
when you're doing the partial fractions, in the left hand side, in the numerator, it should be Z, right? Instead of 1.
Yeah. I mean the yes. I mean you can multiply whole thing by Z, right? Then am I right? There.
Yeah. Yes. Yeah.
Yes. Right. Yeah. So yes. So I think you can do the calculations. Then So 1 over root 5. 1 minus Z squared. Yes, I think it should be here the. Do it the calculation yourself, right? It is not difficult one. I mean, just the calculations, right? Partial fraction method. Then you can show it is equal to this one, right? Yourself. Right now, two new definitions. Let's see. Product of generating functions. Let be two sequences. Let X equal to We yeah respective generating functions. Define Cn is equal to I equals 0 to n ai en minus I, and let Cx let Cx is equal to sigma n greater than or equal 0 to Cn xn. Then Ax Bx sorry. Oh, okay, this is the theorem. Let A and B and be two sequence, X equal that. They are respective generating functions. Define Cn and let Cx equal Cn. They are the respective generating function. Define Cn. Then Ax Bx is equal to Cx, right? In other words, the coefficients of xn in Ax Bx is Cn sigma equals 0 to n ai en minus I, right? Of course, so in the definition that the bunch of notations there, but it's a very simple thing. You can see actually the proof. You can write it for the. I will show the just the idea of the proof. So Ax is equal to what? A n xn Bx equal to B n xn. So you can see A n xn. This is Ax Bx, right? And there. Right. Now, what does that mean? A naught plus A1x plus. Now, this is, we are writing Cx, the product of those two. And so on. And you must multiply it by Right. So now the constant term, if you must multiply these, so the constant term is A naught, B naught. The coefficient of X is what? A1, B naught. And also there is another one, A naught, B1. Now, if you find the coefficient of X squared, what are those things? X squared, A naught, B2. So here, these are the coefficient of X squared. A naught, B2 plus B naught, A2. And also, you can get the X square by multiplying A1X by B1X. So it is equal to A1, B1, X squared. If you need the third one also, let's find the coefficient of X cube. First one is A naught, B3 plus second one A1, B2. Sorry, A naught, B3 and B naught, A3. And then another X3. How you get? X times X squared. A1, B1. And another one, X cube term, you can get B2. Sorry, A1, B2. And the next one is B1, A2. That's all. Right. So now you can see that xn term. You can get xn terms by this ai bn minus I. And I equal 0 to n. Ai. Yeah. So that is the proof of that one, right? Yeah, ai bn minus I equals 0 to n. Okay, another definition. Composition of generating functions. Let fx equal sigma n greater than or equal 0. And let G be a formal power series with constant term 0. Then we define FGX. N is equal to F0 plus F1 GX plus F2 GX squared okay, that's it. We completed the today's lecture. Of course, I will posted the tutorial by Friday, and I will let you know, right? And
Okay,
next time, definitely we will have a quiz.
From
Right,
which lesson, sir?
Which one? The quiz. Quiz
yeah,
on
yeah.
actually quiz on both. I mean,
Okay, sir.
usually the generating function and the recurrence relations are those are closely related, right? So the next quiz is on both the generating functions and recurrence relations, because you can see, right, both are closely related. We cannot study the individual, right?
Okay, sir.
Okay. So, any questions?
No, sir.
Okay, then we can stop. Actually, I couldn't I couldn't mark your past tutorials because I also had the corona whole family. So again, the very unaika. Yeah, come on. Then malabana satya na ko take a balla din.
Okay, sir. No problem.
Thank you.
Thank you, sir.